Welcome to the NHERI SimCenter's Live Expert Tips. In this session, we will introduce you to high-fidelity regional seismic risk and recovery assessment. Our expert today is Laxman Dahal. Laxman is a PhD candidate at UCLA in the Department of Civil and Environmental Engineering. His research aims to advance aspects of the performance-based earthquake engineering framework. His work includes quantifying uncertainty in fragility parameter estimation, developing an end-to-end automation pipeline for the FEMA P-58 methodology, and developing efficient strategies to scale the P-58 methodology to perform regional scale risk assessments. Laxman, thank you for being here.
Thanks, Matt, for the introduction, and thank you for the opportunity to present my work during this webinar. So yeah, today I'll talk about high fidelity, high resolution regional risk and resilience assessment frameworks and how we leverage automation, distributed computing, and some of the open source softwares developed by SimCenter to do large scale computations. And I would like to thank my collaborator, Professor Henry Burton, who is also my PhD advisor, and Conchi Zhang, who helped us with the R2D hazard simulation part. So this is the outline for today's presentation. First, I'll paint the picture as to why we're doing regional scale assessment and why that seems to be the trend in research as well as in practice, and rightfully so. And then I'll go into the core of the regional risk framework, the high fidelity framework that we are proposing, and then go talk about hazard simulation part, specifically the regional scale simulation. Then I'll present a case study implementation where we're looking into about 15,000 single and multifamily residential buildings in the city of LA. And finally, I'll provide some strategies to further enhance the computational efficiency when doing large-scale simulations. So this is the disaster management continuum that we all know and love, right? So it has 4 different phases. And if we look a closer look at these phases, one thing that connects all of them is that it requires regional scale analysis and assessment, right? So for instance, in preparedness, if we wanted to identify vulnerable neighborhoods, we would have to perform regional scale assessment instead of building level assessment, right? Similar cases for response, recovery, as well as mitigation. So for instance, if we wanted to evaluate the prospects of recovery-based design framework, then we would want to do that at a regional scale so that we are targeting certain level of community resilience instead of doing it in a silo at an individual building level. So regional scale assessments have been in practice and in research for many years. One such popular method is HAZUS, published by FEMA. So HAZUS is a pretty efficient tool that leverages predefined building level fragilities, right? So, and it performs risk assessments at an aggregated losses at an aggregated level, right? So for instance, census tract or a zip code level. But to do some of the tasks that I described in the previous slide, for instance, recovery-based design, we wouldn't be able to use tools like HAZUS to do that. So for that, we are proposing what we are calling modern regional risk assessment framework, right? So some of the properties of the modern tool would include high fidelity, right? So we should be able to explicitly model the components of the building, model the structural parameters of the building, as well as include spatial correlation and be site specifics, right? And so that would enable us to include interdependencies and impeding factors as well. So what is high fidelity, high resolution risk assessment framework? Before getting to that, I want to first establish the definition of this, some terms that I've been using and will be using for the rest of the presentation. So by resolution, I'm referring to the level of detail and accuracy in a map, right? So from the regional assessment frame perspective, the the highest resolution that you can have is site-specific analysis, right? So that's per building across a region, and you could aggregate across neighborhood and zip code. And as you go, as you zoom out further, you lose the level of resolution, right? And by fidelity, I'm referring to the level of detail in structural modeling, right? So in this case, I'm loosely referring to the dimensions as the level of fidelity, but obviously it would include the detail of the material parameters that goes into the numerical model as well. So fidelity refers to the detail in structural numerical model, roughly. And the other term that I'll be using is the FMA. So that refers to fully mechanistic assessment. So that assessment follows FEMA P-58 methodology, right? So it goes through hazard simulation and creates structural model and performs everything explicitly, defining even the components at per building and per floor level. So yeah, those three terms are the terms to keep in mind. So the proposed framework has six different steps. So the first and trivial step is to identify the region and building inventory, right? So once you have the building inventory and the region, then we would want to model the exposure and model the seismic hazard. So these two steps do not necessarily be in sequence, since these two steps are independent, so they can be performed either one in any order, as long as you model the exposure, right? So you model what buildings you have at each site, and you model what is the anticipated shaking intensity that you're expected to see at that particular site. So once you have the building and exposure modeled, then we apply some kind of filter. And the goal of this filter is to identify similarities between sites, right? So for instance, across a region, there could be two sites that have a similar building and that is expected to see similar shaking intensity. So instead of performing explicit FEMA P-58 type of analysis for two different instances, we would only perform analysis for one and use the information from that to represent the losses at the other one. So that way we reduce the number of explicit analysis that we can perform while still maintaining the high level of fidelity and resolution. And so once we identify the number of unique runs that we have to perform across a region, right, then we implement AutoWood SDA, which is an end-to-end automation tool that I'll talk about in the next slide, and use that along with the distributed computing to scale that computation for thousands of buildings, right? And the output of that process would be the site-specific distribution of losses across however many sites that you have within the region. So this is the overview of end-to-end automation tool, AutoWood SDA or Wood SDA in short. So one end of the computation is inputs, right? The set of user inputs, which includes site-specific information such as latitudes and longitudes, building-specific information such as footprints, the material type, layout of the shear wall, as well as the ground motion sets that you would use to run the dynamic analysis. And the output, the other end of the workflow is the output, which can be any loss parameter that you would want. For instance, collapse fragility, the loss curve, distribution of functional recovery time, and so forth and so on. So there are 4 steps in the end-to-end workflow. The first one is to take the building information and site-specific information and design a code-compliant, create a code-compliant design. And using that design, we create a 3D OpenSys model. We import the ground motion sets and run the dynamic analysis, perform building level damage assessments, and then use automation tool to populate the components into the building, and use Pelican to perform economic assessment, and also the ATC 130 functional recovery time to perform the functional recovery analysis. So you might have noticed that the four frameworks, four methodologies follow the FEMA P-58 methodology as shown on this slide, right? So for instance, the structural analysis closely mimics the structural module that I presented on the previous slide. So why do we need automation, right? So FEMA P-58 methodology is, as we know, pretty tedious to apply and implement from scratch, right? So this table roughly shows the time it would take me with my level of expertise to perform explicit analysis by creating the structural model and stuff like that. And as you can notice, the most time-consuming part is the structural analysis, right? So creating the numerical model and running analysis is the most time-consuming part. And if we wanted to scale that for a region with tens and thousands of buildings, that method would be unfeasible, right? So we basically wouldn't be able to perform regional scale assessment. With SDA as a standalone tool, we would reduce the computational time significantly, but not enough to make the computation feasible without super computers, right? So, and one of the most time-consuming part of Wood SDA as of this point is input data preparation. So, since we design code compliant design within Wood SDA, so it requires explicit configurations of shear walls to be defined so that it can design those shear walls, and that takes about 3 to 6 hours. But in this study, what we did is we predefined a database of design variants that I'll talk about in the next slide, so that we don't have to spend that time preparing the data. And with the predefined database, the Wood SDA is not only computationally feasible, but also iterable if we wanted to do like sensitivity studies for recovery-based design. So I won't go into the detail into what went into the development of this design variant database, but we created a database of kind of like archetype building, but these buildings only have the shear wall locations and length defined, but they have not been designed yet, right? So we included 4 different parameters: number of stories, different floor layouts, seismic weight, and all of these layouts have been well studied in the previous in the published research topics, such as the FEMA P-2139 study, which was a part of the ATC, which was the product of the ATC 116 project. Right, so once we have the automation tool figured out, then we move on to the distributed computing. We use HPC cluster in 2 major ways. So the first one is to implement the Wood SDA in distributed computing setting, right? So each of the computation of Wood SDA for one particular building is independent of one another, right? So even though the assets are distributed spatially, the computation itself is independent. So there is no input or output data flow between different processes, which allows us to exploit the distributed computing framework and not be constrained by any computation limitations, right? For a hazard simulation, we utilize R2D, as I mentioned earlier, and we use parallel computing. And the main difference between the distributed and parallel computing, the way we're implementing, is in the parallel computing, there's input and output data flow between the number of processes and the compute node, and the root node and the compute node, which is not what we have in the distributed computing. Right, so now I'll talk about briefly go over the regional hazard simulation part using R2D. So we used R2D's backend code to perform the regional scale hazard simulation. It involves 5 major steps. As the first one is to identify or generate the earthquake event set. In this case, we used USERV3 mean model, which contains about 350,000 possible scenarios. So using that, we downsample the earthquake into a manageable set, right? So in this case, we downsampled 300,000 to about 20 scenarios using the Davidson's method, which I'll briefly touch upon in the next slide. And then for each scenario, we simulate correlated ground motion maps, right? And then we downsample the total ground motion map to, again, a manageable size. And all of these processes are done using R2D backend code. And finally, the fifth step is to select the ground motion records, since we're using Autowood STA to perform explicit analysis per site. So we need to select ground motions per site. And even though R2D has a built-in ground motion selection tool, we developed our own in-house to incorporate some of the previous research that we have done in this topic. So to give a brief overview of the OPS method, right? So the objective of the OPS method is to match the true hazard. So that's the hazard that we get from the USGS hazard API with the hazard that we recreated from the downsampled set of earthquake events, right? To do that, it has 5 steps, and it utilizes mixed integer optimization routine, where it loops over all the number of sites and all the number of return periods that you specify, and minimizes the error as it downsamples the population set to the reduced set of earthquake events, right? So this is an example of one example site at site 0. Of the maps that we simulated, right? So on the figure on the left shows the full stochastic set, 800 maps. So we downsampled 20 scenarios, and we simulated 40 maps per scenarios. So we have 800 maps in total, and we downsampled that map to 60 maps. So the figure on the right in the black line shows the target spectrum, right? So those are the 60 downsampled maps, and then the red line shows the spectrum of the selected ground motion record for those 60 maps. So we implemented the high fidelity, high resolution framework for our case study, looking into about 15,300 new single and multifamily residential buildings, right? So these buildings were permitted to be built since 2013, and that data is publicly available in the LA Open database. So the figure on the right shows, along with the timestamp, the buildings that were permitted over the years. So to model exposure, we take the previously discussed database of design variant. We randomly sample that design variant to one of each site across the region, right? And we use the design module of the Wood SDA to create the design. We repeat that process across the region, and so this plot shows the distribution of those distributed buildings across the region as a function of the building layout, right? So since we randomly sampled from the database, the distribution looks uniform, which is what we expect. So I won't dig into the detail of the result as well, but these 2 plots show the loss curves. The figure on the left show the loss curve of the loss ratio, right, of 15,000 buildings, and the figure on the right shows the loss curve for the functional recovery time in days for all the 15,000 buildings. So one of the things that we can do from those loss curves is we can take a stripe out, right? We can at certain return period level. So the figure on the left shows the spatial distribution of that stripe at 475-year return period. So it shows the spatial distribution of the expected loss ratio. And the figure on the right shows the total loss. Right. So one of the good thing about repair cost in terms of absolute dollar amount is that we can add it up to compute the total expected loss across the region. And it looks like for a 475-year event, the total loss accounting for the single family buildings would be roughly around 7 billion US dollars. And we can do the similar thing for the functional recovery time as well. So the figure on the left shows reoccupancy time, and the figure on the right shows the functional recovery time in days. So in terms of the runtime, to compute the regional hazard, we spent about 320 CPUs, and it took us a little bit over 3 days to complete the computations. As for wood SDA, it took about 64 hours with 400 CPUs. And as I noted earlier, one of the steps was to identify the redundant sites, right? So we had 15,000 sites, 15,336 sites, and it looks like out of that, 131 are redundant, right? So as we the reduction seems a little bit low considering the total sites that we have, but since our goal was to maintain high fidelity and a high level of resolution, the reduction is lower. But in the next few slides, I'll talk about how we can play around with different approaches to reduce the number of runs that we have to perform. Right, so in terms of the computational challenges and the computational aspects of running these large-scale simulations, hazard simulation is a memory-intensive task, right? So it has to, for 15,000 sites, you have 15,000 by 15,000 matrix, and you have to include the correlations in the shaking intensity across the sites. So the computations that you have to do increases exponentially as you increase the number of sites. But that's not the case in the end-to-end fully mechanistic assessment using wood SDA because the computations are independent. So the runtime scales linearly, roughly speaking, as we increase the number of sites, as well as we increase the number of CPUs and the number of ground motion records per building that we run. So running large-scale simulations like this came with many different challenges of its own. One of the biggest challenges that we faced was the convergence issue in the OPS method, right? So as I mentioned earlier, the OPS method loops over all the sites to minimize the error. And with 15,000 sites, looping over all the 15,000 sites didn't converge for us, right? So what we did is we instead grouped those 15,000 sites into 108 k-means clusters, and then we took the centered location of those clusters and used those centered locations as a representation to reduce the number of maps as well as the number of earthquake scenarios in the OPS-based method. The other solution that we implemented was we lifted the runtime cap, right? So in SimCenter, some of the SimCenter tools, you have runtime cap built into to limit the resources right to 60 minutes. So we lifted that and let it run until it converged. Another issue that we faced was the timeout issue in the USGS hazard API, right? So reducing the number of sites to 108 kind of solved that. And we also increased the buffer time on API so that it doesn't time out while we're running the analysis. And the third one was probably the biggest one to kind of figure out and solve is the parallel computing input-output bottleneck, right? So R2D uses OpenMPI to parallelize the computations, which is pretty efficient for small scale analysis, but for large scale analysis like 15,000 sites, whenever you put computations into the compute cores, right? So each compute core performs Monte Carlo simulation to generate the map, right? So when you transfer those huge data sets data files between the compute node and the root node, the memory allocations within the root node was not able to handle the data that was being transferred back. So we discretized the execution into 4 different batches with 5 scenarios per batch. So that's how we were able to run all 20 scenarios and get the stochastic set of maps. So how can we increase the computation, right? So we view regional scale assessment as a trade-off between fidelity, resolution, and efficiency, right? So we roughly break it down by resolution and fidelity as I prefaced earlier. For resolution, you can perform a very high level of resolution, right? So we can define the building at a very high level, and as well as the same for hazard, right? So that would give us the high level of resolution that I presented in this study. But if you wanted to give back, if you wanted to trade off some of the resolutions, right? So if you wanted to define the buildings at a bin or a cluster level, so if you wanted to do that, you would end up with like 6,000 buildings, 6,600 buildings, right? So that's 1/3 of the total inventory that you started with. If you wanted to reduce the resolution even further to like cluster instead of bins, right? Or increase the number of cluster, then you'd get about 1,700 fully mechanistic runs that you have to deal with. So by kind of playing around with different levels of fidelity and resolution, you could control the level of efficiency, and obviously that would be reflected in the robustness of the data that you'll get. But this will indeed give you the efficiency that you're looking for. Another approach that we're exploring within our research group is leveraging the powers of surrogate modeling, right? So we have all of these rich data from high fidelity assessments. So we can use that to develop surrogate-based models, and then use that surrogate-based model to replace the computationally extensive part of the FEMA P-58 methodology, which is the structural analysis part, right? And then perform the downstream loss analysis to get the regional loss. So this is another part of the work that's currently undergoing at our research group. And finally, I'd like to acknowledge the UC HPC program, UCLA Hoffman cluster for all the HPC resources that we've been using, and the NHERI SimCenter, all the tools that they have developed and we have implemented in our framework. And I can take any questions now.
Great. Thank you, Laxman. That was really interesting. Very detailed and a lot going on in this framework that you've worked on. We have a couple questions for you. You studied wood frame construction from 2013 and on. How applicable is wood SDA to older construction?
Yeah, that's a good question. So when we developed the database, the design variant database, we included some of the existing materials that you might see in existing buildings. So even though the building designs code compliant design per the code of 2016 ASE, it would still be applicable in some of the existing construction as well.
Okay. And is wood SDA available to others?
It's currently under review, so once that process is done, it'll be publicly available.
All right. You mentioned that the R2D tool has a ground motion selection capability, but you chose not to use it. Can you explain why?
Yeah, so in our previous study, that we looked into, we found that ASI was the optimal IM for some of the buildings that we're looking at, specifically wood frame buildings. So we wanted to incorporate that into ground motion selection process instead of SAT1, which is typically what R2D does. So yeah, that was the major reason that we decided to kind of develop our own.
Okay. And then going back to your computational challenges near the end, you said you discovered this input-output, the I/O bottleneck. How did you discover that? How did it become obvious that there was a problem?
It was kind of trial and error, so we thought it would run. So we let the whole set run for about, I don't know, I would say about 5 days, and it just didn't finish running. Right. And since it was jammed, the data was jammed, we weren't getting any errors because there wasn't any computational error, so to speak. So we kind of did trial and error. We reduced the number of sites. We did like 10,000 sites, still errored. We did 5,000 sites, it ran. So we thought maybe like the data input output is the problem because computationally there is no error. So yeah, it was kind of, that's why I said it was the hardest one to figure out, because we didn't quite know what was the issue that was leading us to not get the result, but the code itself was fine.
Okay. And still sticking on this slide, this in the converging issues with the OPS method, you said that you lifted a runtime cap. Where is this runtime cap, and how long did you have to extend it for?
So I think that was one of the built into R2D backend. I think it was set at 60 minutes, so we lifted it until it converts. So we basically lifted the constraint and runtime and let it run until it converts.
Okay. And then if we go back to the downsampling of your hazard maps, I think the question is a little bit more about the importance of that, or how you went about selecting 60 as your target number for downsampled set, your downsampled set. How did you know that was a good number, or how did you arrive at it?
Yeah, so that's a good question. So one of the constraints that we had was we wanted to limit the number of ground motion, because that would increase the computational time, since we're running OpenSys analysis with those ground motions. Right. So we started with 40, and we kind of did like a sensitivity study. So we did 40, 50, 60, 90, 100, and I think that's how high we got. So we basically compared the KL divergence between the population set, which is the 800 maps, against the downsampled maps, so the set of downsampled maps, and 60 seemed to be the sweet spot. So it had low enough KL divergence against the full set, but it didn't impose that much of computational burden on wood SDA. So that's how we got to 60.
Okay, fantastic. And the last one isn't, well, maybe a little bit of a question on your surrogate modeling that is maybe some next steps. If you aren't familiar with SimCenter's UQ office hours, Fridays at noon Pacific time, the SimCenter has office hours with two of our researchers in residence who may be of assistance to you if you need some guidance or help using our tools for that. And you can register for those office hours or sign up for those on our SimCenter forum under the UQ or QuoFem channel. I'll put a link to that in the chat in a minute. But Laxman, thank you very much for your presentation and taking the time to answer our questions. I think it was a really interesting presentation. I think a lot of us are looking forward to seeing the wood SDA go through its final reviews and be available to others if you're intending for that to be the case. To those who attended live, go ahead.
I was gonna thank you for the questions and and again for the opportunity to present my work.
Great. To our attendees, thank you for joining live. I want to remind you, you can register for SimCenter events on our webpage, which is simcenter.designsafe-ci.org. And this concludes today's live expert tips with the NHERI SimCenter. We hope you've been inspired by the research presented and can benefit from its adaptation or reuse in your work. Again, thank you very much, Laxman.